All right, let's start. Yeah, today I'll use this mic. Okay, so we are so we are currently studying in the third chapter in orthogonal kind of stuff. So we consider some subspace W, and then its orthogonal basis. And then at the end of the last lecture, we discussed about the orthonormal basis. And then if we have a orthonormal basis, let's see. Okay. So the projection of some vector y onto this orthonormal basis spanned by u, for example, in this case, so we can remove this denominator because the length of orthonormal vector is 1. Okay, so it is simplified by this kind of formula, right? So okay, so again, W is spanned by U1 and U2, and maybe more vectors, but let's just use 2 vectors, U1 and U2, and they are orthogonal to each other, and then their length is 1. And then in this case, given a vector y, you can compute this projection of y onto this subspace W as what? U inner product with the y inner product with the U1, and then this is a U1 plus y inner product with the U2 and U2, right? And so in this case, so this guy was y transpose and U1, and altogether this becomes a scalar, and then we have U1, right? And then also y transpose and U2 and U2. Okay, and then this can be viewed as a linear combination of U1 and U2. And what is the coefficient? This part, these two parts are the coefficient. And then let's change this form into a vector equation form. So what we do is, so we want to have something like this. Okay, so what will be our matrix A? And that matrix will be this U1 and U2. This is our co-matrix. And then what is the linear combination coefficient? Those two. So this guy will be y transpose U1, and this guy will be y transpose U2, right? And then let's change the order within this inner product as U1 and y, U1 transpose y, and U2 transpose and y. So we can certainly do that because we know a inner product with B will be the same as B inner product with A, right? Okay, so far so good. Okay, and then we consider this kind of vector, column vector, right? And then this guy can be further factorized out as U1 transpose and U2 transpose. And we've formed this one big matrix, and then we have y here. Okay, so can you verify this vector is equal to this, right? So we now have another big matrix, right? And then a column vector on the right. And then if you compare the first element, and then we will obtain this guy times this to obtain this, right? And so on. Okay, then this part is the same as this part. And then we have one big matrix U here. Let's call that as U, whose column is our orthonormal vectors or orthonormal basis for our subspace W. And then we have here as U transpose. So this can be viewed as the transpose of the entire matrix U. And then we have this Y. And altogether, it can be written as this. Okay? And then this part is this linear combination coefficient. But we can switch the order by computing this guy first and this guy. Okay? So, although it looks almost the same, but how we compute it is a little bit different. So, in the previous case, we first do the inner product with this U1 and Y and U2 and Y. And that way we obtain these scalar coefficient values. And then we linearly combine these two basis vectors by using those linear combination coefficient. But in this formula, the computation is as follows. We form this really big matrix. It can be really big. And then after computing this matrix, and then we simply multiply this matrix vector product. Okay? Okay, so let's just rewrite this guy. So proj W or Y, where W is spanned by U1 and U2, and this guy will become U and U transpose and Y. Okay, and then let's view this guy as some kind of function, linear function f, where the input is vector y. And then if this transformation or this function was linear, and then we can view it as a kind of matrix times vector multiplication. And what is this A? This one is this guy. Okay, so this guy or this matrix can be viewed as a kind of linear transformation that projects any vector y onto this subspace W. And this subspace is spanned by the two orthonormal vectors. Okay? Then let me ask this question. Can we obtain another set of basis vectors that are still orthonormal? So this subspace W, suppose this subspace W is spanned by these two vectors, and they are orthogonal to each other. Okay, and then their length is 1. So this is an initial point. Can we obtain another set of basis vectors that are still orthonormal? So the span will be this kind of a plane, right? And then let's just simply rotate them a little bit. And then we will have two different vectors. And they still form, or they will still span the exact same subspace. And then they are orthogonal to each other, and then length is still 1, right? We just simply rotated them slightly. Okay? And then the subspace is still the same. And then suppose you have one vector y, and then you projected it onto the subspace. And then in that case, you are projecting that onto this plane, right? This plane, when projecting this guy onto this plane, you don't even need to think about what the exact bases are for these subspace, right? This orthogonal projection is automatically defined if you have a particular subspace, right? And it means suppose you found another orthonormal vector as maybe v1 and v2. Okay, and then let's imagine it's an orthogonal projection onto the subspace W, and then in this case our matrix U will be this guy, right? This will be our new matrix V, which is composed of different set of basis vectors. Okay, in that case, still, from the perspective of a linear transformation or the function that does the orthogonal projection onto this exact same plane, okay, in that case, this matrix A should still be the same, right? Because regardless of which particular set of basis vector, if your subspace is fixed, and then for one particular point, its orthogonal projection will still be the same point, right? And then whether using these two, one set of vectors and the other set of orthonormal vectors, and then this point should still be the same. So in this case, this A should be the same, right? That way we will have we will have exact same result in this vector. So it means this V times V1 and V2, and then their matrix product of V and V transpose will be the same as U transpose, right? They should be the same, right? From our thought experiments, right? Our intuition or understanding is saying that this should be true. Okay, so let me give a simple example of observing or checking this fact or this property. So let's just simplify our subspace as our entire subspace. Our entire space is a three-dimensional space, x, y, and z. And then let's imagine our subspace is just the x and y plane, which is a flat plane. Okay, not having any angles along the z direction. And what is the simplest orthonormal basis for that subspace? It will be 1, 0, 0 and 0, 1, 0. Right? So it is like a unit vector along the x and unit vector along the y, not having any vector along the z. Right? So this will be one orthonormal basis vector for this flat subspace, horizontal subspace. Okay. Okay, and then let's imagine some vector y, and then what will be the orthogonal projection of this y onto this subspace, proj W of y. What should be that vector? So we have x and y and z, and then we have 2, 3, 4, and then we projected it onto this horizontal plane, right? X and y and z. What should be the coordinate? Or what should be that vector of this orthogonal projection? 2, 3, 0, right? It should be quite simple, right? And then let's just apply this guy, U and U transpose and Y, and then let's just verify if that is true. Okay, and then these two are our orthonormal basis vector, and then 1, 0, 0 and 0, 1, 0 will be our U. And what will be U transpose? 1, 0, 0 and 0, 1, 0. Okay. In this case, we will have 1, 1. Yeah, so if you compute like this, and then we will have this, right? And this guy and this, and we will have this, right? And so on, right? So, yeah, our linear transformation that projects this, that does orthogonal projection matrix of U transpose will become this guy, right? And then if you have 2, 3, 4, and then it is just simply making the z coordinate or the third dimension as 0, right? Okay, and then let's think about another also normal basis vector. So instead of 1 0 0 and 0 1 0, I'm gonna just rotate them with the 45 degree, and then 1 0 0 will become this and this, right? So this one will be like a rotated version of our kind of a new basis vector that are still also normal, right? Okay, so this one will become our new V, and if you compute V transpose, it should be still 1 0 0 0 1 0 0 0 0. Okay, so yeah, so it's a tedious computation, but minus 2. Okay, so if you quickly verify with your brain, then it will give this kind of matrix as the same one as the previous one. Okay, so here one insight or one kind of understanding that we can obtain is when doing the orthogonal projection, the particular basis doesn't matter. I mean, regardless of what particular basis you are using, the orthogonal projection is determined as a unique point, right? It's just a matter of like a different linear combination of using different set of basis vector. So it's like, so if we imagine this kind of plane and then this kind of orthogonal projection, and then suppose your plane was this, and then we have point y here, and then we have y hat, and here we have an origin here. And then suppose your basis vector was this guy and this guy, and this was your one particular basis vector. And then you first do orthogonal projection onto this basis or this direction, and then you do another orthogonal projection onto here, this line, and then direction and the magnitude, and that way you can represent these two vectors, and then after summing up, and then you will always have this y hat. And now let's imagine another set of orthogonal vector. Suppose your one vector was this guy and maybe this guy, and still this is a 90 degree, which is orthogonal to each other. And in this case, it's a little hard to draw because it's a three-dimensional case, but this guy is projected over here, and this guy is projected over here. Yeah, sorry for bad drawing, but so after adding these two vectors, and then this guy will become this. So yeah, it's a three-dimensional view, but if we look at it as a kind of flat view, it's just like this. So we have this kind of two-dimensional plane, and this guy is like 3, 2, and then it's 1, 0, no, it's 1, 0, and 0, 1, and then we can think about the linear combination. Like this, right? And then there's some. And then what about having another linear combination like this and this? This is our new orthogonal basis. And then this one will become your new axis. So we imagine these two new axes, and then this guy and this guy. And then still you will have this rectangle, right? So the direction changed from this horizontal direction to this slanted direction, and then their associated or their corresponding linear combination weight or the length has changed, right? But still, they will form this exact rectangle to form your original y hat, which is an orthogonal projection. Okay, so that way we write the subspace W, which is regardless of a particular basis. Okay, it's not determined by your particular basis, but it's uniquely defined by your subspace. Any questions? Okay, then that's it for third chapter. And then let's move on to the determinant. So I believe you guys watched the online videos, online lectures about the determinant. And yeah, any questions you guys might have? Yeah, please feel free to ask any questions about it.
디터미넌트 A랑 디터미넌트 A 트랜스포즈 같다는 거를 증명을 그냥 보고 있어요. 어떻게 나쁘지? 그거 말고
그거를 이제 어떻게 증명했냐고요? 네. So we had two lectures, each of which is taking about 50 minutes. And then the first lecture was about 10 different properties of determinant. And then, so what's interesting in the determinant, I mean, especially different from your textbook is, so it didn't give any particular definition of the determinant yet, but it just started from the three properties that the determinant should satisfy, right? So this is our starting point, and we kind of promised that we don't even know what the determinant is, but let's just promise that, or let's just agree that the first three properties should be satisfied. Okay, and then using these three properties, which is like the determinant identity matrix is one, and then row exchange will change your determinant, the sign of your determinant, and then these two other properties, which looks like a little bit of a linear combination kind of properties. Okay, and then it proved, or it extended all the rest until up to these 10 different properties, right? Starting from these three. And then, yeah, let me ask a question related to the student's question. Which one was not proved in this lecture? Which one was not proved? Which one was not proved? Yeah, what was not proved at all is, who said 9? Good. This guy. Okay, so the professor at MIT didn't even mention about how to prove, or yeah, not even saying that okay, we are not going to prove this, right? So at the time I watched these videos, yeah, I was a little confused, and then I had to look at the book written by the exact same professor. Yeah, so yeah, I will not also prove. Yeah, I will not give a proof for this. And if you are interested, and then you can look for the linear algebra textbook written by the same guy whose name is Gilbert Strang. And then that book provides two different proof, but both of them are not very intuitive. So, and then also they are using some kind of inductive kind of proof, right? Inductive proof, induction, mathematical induction. What is that in Korean? Mathematical induction. 네, 수학적 귀납법이죠. Induction means 귀납법. Okay. What is the antonym of 귀납법 in Korean? What is the opposite word of 귀납법?
연력.
네, 연역. What is the corresponding English word? Deduction. Deduction. So induction versus deduction. But anyways, so this guy was not proved, but your book is kind of showing or providing some proof through this elementary transformation. But yeah, this is not also fully intuitive. So let's just take it as granted. Okay. And then the student's question was about this number 10. Determinant of A transpose is the same as determinant of an A. How can we prove that?
A 트랜스포 L분이 하면은 A 트랜스포 곱하기 L 트랜스포가 되는데 그 트랜스포를 어차피 다이아고널만 가지고 있으니까 그거를 디터미넌트에도 결국 같아진다는 거죠.
맞아요. 네. Okay, so as the student said, we are utilizing the LU transformation. Okay, so in order to prove this, we first imagine matrix A is decomposed into this L times U as a LU transformation. And then, okay, so let me ask this very basic question: is determined? So is determinant determined for square matrix or also for rectangular matrix? Or in other words, does a rectangular matrix have any determinant? Or does so is it defined for this determinant for rectangular matrix? So what is the determinant of maybe 4 by 3? So it's just our initial starting point and our agreement. It's not a right or wrong answer, but we only define the determinant for the square matrix. Okay, so we don't talk about at all. We don't talk at all about the determinant for the rectangular matrix. We only discuss about the square matrix. And then, so let me just remember what was this LU transformation. In this case of an LU transformation of maybe 4 by 3, what is the size of an L and U? So yeah, let me get back to this rectangular matrix. What is the size of an L and U? L is, of course, it starts with the 4 and what? 4 by 4, right? So L is square matrix, and what about U? 4 by 4 and 4 by 3. So U will have the same size as your original matrix A. Okay, then what is the diagonal element of L? All ones, right? All ones. Okay, so in the case of maybe 4 by 4 matrix, because we are talking about the square matrix, right? We talk about the square matrix in order to discuss its determinant. And so in that case, both L and U will have the same size of a 4 by 4, right? And in the case of an L, it is a lower triangular matrix, and also the diagonal entry are all ones, right? And in this case, let's see. Let's say we have maybe like this kind of a matrix U, matrix L. And what is the determinant of this matrix L? This one, and it comes from this guy. The determinant of triangular matrix is a product along the diagonal, and diagonal elements are all ones. And how can you prove that? How can you prove that? What? Yeah. So we do row reduction, right? Row reduction to convert or change them into diagonal matrix, right? And then what kind of row reduction are we using here among the three? Row replacement, right? row replacement. There is no need for scaling and interchange, right? Row replacement. Row replacement doesn't change your determinant. And why? Doesn't change your determinant. And why? Can you prove that? Row replacement doesn't change your determinant. Can you prove that? No, you cannot prove it. And I cannot also prove it. Because that is our initial agreement of, no. Can we prove that? Yeah, we can prove that, but that kind of proof, yeah, which properties are we talking about? We are talking about this kind of property, which is a fifth property, right? So I was wrong. We can prove it, and so this is exactly the form of row replacement, right? Because it's from this second row, we are subtracting the t times the first row, right? In this case, by utilizing this two properties in the third one that we kind of agreed to be true, right? And so that way, we can prove that the determinant doesn't change at all. Okay, and then we can reduce by using some sequence of a row reduction. By using row replacement, we can change it into diagonal matrix, and still the diagonal entries are all ones. And then it becomes identity matrix, and so the determinant will become 1. So we can we can remove. Yeah, so if we have A becomes L and U, and from the property that we didn't prove, which is a property 9, and we know this guy is the same as this guy, and then this guy will always become 1. Okay? Oh, sorry. So the determinant of an A is the same as determinant of an U, right? And then U will be still 4 by 4 matrix, and this U will have something like this, right? And so still it's a diagonal matrix, and so it's simply the determinant is the product of all the diagonal elements. And then let's think about A transpose. And we still didn't prove that the determinant of an A is the same as determinant of an A transpose. And so we start separately from A transpose and its determinant. And then A transpose will become U transpose L transpose and its determinant. And then we are using the property 9 again, and then U transpose, determinant L transpose. And L transpose will still be diagonal matrix, but instead lower triangular, it becomes upper triangular, and then diagonal elements will all be 1. And so this guy will be having the determinant of 1. And then this guy is just the transpose version of this matrix U. Okay? In that case, this guy, becomes lower triangular, but still diagonal elements are remaining the same, and so the determinant will also be the same. And that way we can now have a conclusion that those two determinants should be the same. Okay, and then let me ask this question. What if this matrix U is something like 0, having a 0 on the somewhere along the diagonal? So the question is, what is the determinant where your matrix? Yeah, so your matrix is a upper triangular, for example. So we discussed the we consider upper triangular matrix, and your upper triangular matrix has some zeros like this. And then in that case, what is the determinant? Determinant will become 0, and why? center of the diagonal. Yeah. So if we apply that, if we apply that some item that is saying that the determinant of diagonal determinant of an upper triangular matrix will become the product of the diagonal elements. But in order to prove that, how did we prove that? So we actually proved it by eliminating this guy and this guy and this guy, right? And that way we created them. We changed it to diagonal matrix, right? But in this case, we cannot cancel them out because by using 1, we cannot do anything, right? We cannot multiply 0 with something else to make non-zero, right? In that case, how can we so in this case, the determinant is a 0. That's our conclusion. But why is the determinant of this guy 0? So in this case, so if this guy is kind of our echelon form, so this is an echelon form, right? Our staircase shape, right? But the stair is having like this kind of flat, like a larger flat like area, right? And then it should end here, right? And so originally, if your matrix was something like this, and then let's see. Yeah, and then you can still create this guy as 0, right? And then we will obtain all 0 rows in the corresponding row, right? Okay, and then also, if you have some matrix, yeah. So let's not think about this matrix as our input. So in general, you have some matrix like a 4x4, and then you change it to echelon form. That will become your upper triangular matrix, right? And so if your upper triangular matrix was something like this, and it became flat. And in that case, because we have the same number of rows and columns, right? If we go like a 2 steps at once, and then you should always have a 0 rows in somewhere at the very bottom, right? Okay, so in this case, it's like, so yeah, let's think about another case where we have 4x4 matrix. Yeah, it's just intuitively quite obvious, but let me just give another example. So suppose your matrix was something like this. So you went 2 steps at once. In that case, you will always end up before reaching the last row. So the last row always becomes all 0, right?
So it's not, you can say that's not invertible.
Right. Yeah.
Singular.
Right. So in one of the theorem that we learned in the maybe 2 weeks ago or so, we learned that invertible matrix should be always row reduced into identity matrix, which means identity matrix is a kind of special case. I mean, a representative case where this staircase is always like, yeah, something like this, right? So this jagged, this kind of structure is always like a 1 step at a time, right? And so if we go like this 2 steps at once, and then we will always end up having the last row being all 0. And then all 0 row, the matrix with the all 0 row, and then their determinant will become 0, right? And that was one of the previous property that we proved. Okay, and so back to this U where some diagonal entry contains 0, and then yeah, this guy will become will have the 0 determinant, and so still we can write like a determinant of u as like u1, u2, and so on, where those u1s are, u1, u2s are like all diagonal entries. And so if we see 0 somewhere along the diagonal, and then the determinant will be automatically become 0. Okay. Any other questions? So in the second video lecture, yeah, was also quite important, and that's practically important because you will use a lot in solving some exercise problems. And you guys hopefully you guys understand that, right? So let's see. Let me just check one thing. So suppose you have an n by n matrix, and then it will be decomposed of some summation of how many matrices. So in the beginning of the second lecture, it started with this A, B, C, D, and then it will be what? A0 CD plus 0B CD. So this is the one of the first properties that we promised to be true, right? And then this guy will become like A0 C0 plus A0 0D, right? And likewise, this guy will be decomposed into 2, right? And so it became like 4 different elements. And then altogether, the determinant of this guy is what? The determinant of these 4, right? From the initial property that we had. And then in the case of an n by n, how many elements or how many matrices like this? 2. Where? Yeah. Yeah. So in that case, we are that's after removing this guy A0C, 0. It is like we contain 0 columns, and so in that case, if we transpose it and diagonally flip it, and then we will observe 0 row, right? And that's when the determinant becomes 0, right? Okay, so we can safely remove this guy where we see either all 0 row or all 0 columns, right? So in that case, we can just remove them. And that way we only have like two entries or 2 matrices. But I'm asking, before doing so, how many matrices, which is a kind of decomposed from the original matrix? It's we have a 4 matrix. So in the case of 3 by 3, how many? So it is a exact same example in the lecture. How many? 6? Huh? It should be 27, right? So in this case, we will have like 3 different matrices: A00, 0B0, 00C. Okay, and then each of them will be like split into 3 matrices, right? Because we are moving onto the second row. Second row will be decomposed into 3. So initially we had 3, and then each of them will be split into 3. And then we now move on to the last row, and then we split each of them by 3, right? And so 3 times 3 times 3, right? So it's like 3 times 3 times 3. So in the case of an n by n, n times n times n times n. And then how many entries we have? N to the power of n. which is really large, right? But unfortunately, fortunately, which is a good thing, among those, just like these kind of matrices where the determinant can be trivially be zero, there are many different entries that are having a zero determinant, right? So that determinant is like we distribute non-zero elements on distinct rows and columns, right? So C, D, E, F, G, H, I. So yeah, you guys know this guy is decomposed into 3 to the power of 3. And then we are choosing one element at each row, right? So that way we obtain these different matrices. Okay, and then so we are choosing one element at each row. So we chose this guy. Suppose we chose this guy, and then we chose maybe this guy, and maybe this guy. In this case, we have like 3 cards or 3 options, 3 non-zero entries, and then we have to distribute them over different rows and different columns. And if we don't use a different column, so in this case, for the first entry, we use the first column, and then in the second entry, we also use the same column of the first column. In this case, we have n cards or n trials, right? And then we are distributing n different non-zero elements among n different rows. And so if there is a redundancies among these n entries, then it means there exists at least one column that was not used at all, right? Which means there should be all 0 columns, right? So that way, the corresponding matrix will have a determinant of 0. So that's why we have to distribute among the columns in a non-redundant manner. Okay, so that way we are kind of considering kind of factorial of an n when choosing different columns, right? And then yeah, the remaining formula that was derived in the lecture, yeah. Once you have the clear understanding about this, and then it should be easy to follow the lectures. Let's see. So among these, you will have this kind of homework. Okay. So you will probably, I'll post another homework that is due next Monday, okay, just before our exam. Okay, so let me just think about this kind of matrix. And then in this case, so we can be more flexible. So in the previous case, like this, so we are starting from the first row, right? And then choose those elements that are like distributed over columns that are like in a non-redundant order. But we can freely change, or we can be really flexible by choosing any of our rows or columns. Okay, so in this case, because and why is it possible? Because we can freely change the rows, right? Although when changing the rows, one time of row exchanges will change the sign of the determinant, right? But still, the magnitude or the value itself is not changed at all, right? So that way we can freely choose any rows to start with, or we can even choose any columns, because the transpose of the matrix will still make the determinant remain the same. So the determinant doesn't change at all, even when we use the transposed version of the matrix. Okay, so that means we can choose any rows or columns. Okay, in this case, suppose we are given this kind of big matrix, and then we have to compute the determinant of it. And then the row or column that we are going to start with will be this row, okay, this row, because we see many zeros here. And so in this case, we can only consider this one single non-zero elements along this column. Okay, so that should be your starting point. And then we are suddenly talking about the last formula, like by removing this guy and this guy, right? And then we consider the submatrix, and then consider its determinant. So that way we kind of reduced the size of a matrix that we have to compute the determinant of, right? Okay, so in this case we have to start with this kind of row, this kind of column, because it will have the most number of zeros. Okay, any questions? Any other questions? 어떤 방법이 제일 많이 쓰이냐고요? 그 코팩터 포뮬라. 코팩터 포뮬라로 해야 돼. 그러니까 이거 so yeah, among maybe two or three different formula of the determinant. So practically you will oftentimes you will use a cofactor formula. So this is a kind of exact way of utilizing cofactor formula, because we are choosing one column or row and then consider the determinant of the submatrix. So submatrix was called a cofactor. So that way you can reduce this kind of cofactor, and then suppose you have another kind of pattern of zeros, like maybe 0 and 0 and maybe 0 here. So it has like two non-zero entries in this column, right? So in this case, it will have more number of non-zeros compared to the initial column that we chose, right? So this column should be our still it should be our first choice. And then if we think about the cofactor or the submatrix, okay, and then we remove this and this, and then among in the submatrix, this column which has 0 and 2 and 0 0, so this is 2, so it will have only one non-zeros in this submatrix after removing the corresponding row and column, right? So that should be your next choice. So in that case, you can further, in that case, you still apply the cofactor formula recursively. And in that case, now you are considering, like, after you remove this guy and this guy, and then now the matrix size will become 3 by 3. So now it's much more manageable or much easier to handle. Okay. So you will train yourself in computing the determinant this manner. And then some of the similar questions will be seen also in our exam as well. Any other questions? Okay, then now let's move on to the next chapter. So the next chapter is about this Gram-Schmidt process. So Yeah, at first, it might be quite complicated, but the intuitive, once you have an intuitive understanding, it should be quite easy. So, this Gram-Schmidt process, even before talking about any details about it, so what we are doing is as follows. So the initial starting point is some set of linearly independent vectors. So you may you have maybe 3 vectors that are linearly independent, and then we can think about its subspace W spanned by these 3 linearly independent. Maybe let's call that as x1, x2, x3. So these are the 3 vectors that you have: x1, x2, x3. Okay, and then now we basically change them into a orthonormal basis that spans the exact same subspace. So this is what I already described in the very beginning of this big chapter 6. So you are initially given like 3 different linearly independent vectors, and then you consider the span of it, and then you now want to compute its orthonormal basis that spans the exact same space. Okay, and then in that case, if you remember what I described or what I explained in maybe a week or so ago, how we obtain orthonormal basis is as follows. So we start with the first vector, and then we now consider the smaller subspace that is spanned by only the first one. So this is our final goal or final kind of destination, which is the largest subspace that we consider. Okay, and then now the smaller subspace that we can consider could be like this: W1 spanned by only x1. Okay, only x1. And then what is W2? W2 is spanned by x1 and x2. And W3 is our final destination of this guy. And then is this basis vector x1, is this guy orthonormal basis? Is this orthonormal basis in general? The answer is no, because, okay, so what is the W1? So given these 3 vectors, W1 is just nothing but this straight line spanned by only this vector, right? And then is this orthonormal basis vector? The answer may be no in general, because their lengths might be like a larger than 1 or smaller than 1. So we simply scale them, or by stretching or shrinking them so that the vector length becomes 1. Okay, and then now we form the W1 spanned by the first vector and also orthonormal basis vector. Okay, so far so good. And then we now consider the second one, the second vector. So this is our x2, and then we remove the component, we remove the component that is explained by the previous subspace W1. And how we do it is we just do the orthogonal projection of this second vector x1 along this first subspace W1. And then the remaining part will become this orthogonal vector, which is our remaining vector. Okay, and then we remove, we scale this vector to be having the length of 1. And then instead of these vectors that have some angles other than different from 90 degrees, we scaled it, and then from this we removed its orthogonal projection, and then the remaining part will become this orthogonal part, right? This orthogonal complement, this remainder or U2. Okay, so what we are doing can be described as follows. So you are given x1, and then you just simply normalize this vector like this, and then this one will become also normal basis vector for w1. Okay, and then let's try to compute w2. W2 is computed as follows. So from the x2, we remove the orthogonal projection of this x2 onto the subspace w1. Okay, so let me just highlight this subspace is this guy, which is the subspace spanned by the previous vector. Okay, let's call this vector as v2. And then this v2 is further normalized by its own length, right? So this guy, or this guy, v2 is orthogonal to w1, because that is the residual part after subtracting the orthogonal projection onto the previous subspace w1, right? Yeah, so far so good, right? And then this u2, which is just nothing but the normalized version of this remaining or residual part, right? Okay, so the question is this subspace and this subspace the same? Are these two subspaces the same? So again, like W2 is spanned by these first two vectors, right? So we are thinking about this plane. And then we change it, we scaled it this direction of the first vector, the length of this first vector. And then for the second one, we changed it so that it becomes orthogonal to the first vector, and then we scaled their length, and then still like this, these two vectors will still span the exact same subspace. Okay. Now this is a key point. So this is quite important part. Okay, then let's move on to the third one. So the third one is still going through the exact same process, but still x3 minus, in this case, so what should that be? Should it be W1 or W2 or W3? It should be W2, right? Because we are subtracting out the orthogonal projection onto the subspace explained by the previous two vectors, right? Previous vectors. So we now have this subspace, and then we have another vector that is orthogonally projected onto the previous subspace spanned by these two vectors. So that's called this W2. Okay? And then in this case, how can we obtain this part? This part is written by this. So we have a nice also normal basis for our subspace W2. So it will become like let's see. So okay, so you guys know the formula, right? But let's skip that because it's just a lengthy, tedious write-up of this formula. But let's call this guy as also V3. Okay, let's be still conceptual. So we removed orthogonal projection onto the previous subspace, and then the remaining part will become like a perpendicular to W2, right? And then we still normalize it so that the length becomes 1. So we have this guy as U3 is v3 and v3. Okay, and now we obtain x1, x2, x3 will be the same as u1, u2, u3. Right? So that way we obtain also normal basis one by one, like a sequentially, right? Sequentially by handling one vector at a time. Okay. So this is a Gram-Schmidt process. Gram-Schmidt process. So basically, you want to change the linearly independent set of vectors into also normal basis vectors. Also normal set of basis vectors. Okay. So yes, let me go through these example. So we have x1 and x2 and x3, and then the question is, so they are linear initially. They are linearly independent vector, and then we can easily check them. Then the question is to construct this orthogonal basis vector for W, and then we obtain the first vector as this v1, and then yeah. So up to this point, we only think about the orthogonal basis vector, but let's change it as also normal basis vector. In this case, we have to normalize this x1, right? So this guy should be normalized by 1 over 2, 1 over 2, 1 over 2, 1 over 2. So in this case, the length will become 1, and this guy will become u1. And we from now we move on to x2, and then subtract it from subtract this orthogonal projection, right? And then the orthogonal projection, the formula is this, right? And so we obtain this, and then this guy is normalized so that the length becomes 1. Okay, and then let's move on to the third vector. And then now this orthogonal projection of x3 onto w2 will now involve two basis vectors. So instead of using u1 and v1 prime, let's use u1 and u2, which is a normalized version. And then so there is a typo here. So the formula is this guy, right? So this is an orthogonal projection of this x1, x3 onto u1 and x3 onto u2, right? So in the denominator, we are dividing it by u1 and inner product with u1. But if we obtain nicely normalized vector, or the unit vector, or the length, the vector of the length 1, this denominator will become 0, right? Become 1, right? So in this case, this guy will be automatically b1. Okay, anyway, we obtain this residual vector that is orthogonal to the previous subspace spanned by v1 and v2, or u1 and u2, which are normalized version. And then this is a orthogonal projection, and then we are subtracting it from the original vector x3, and then this guy is the resulting residual vector, and then we can also normalize it so that we have the length of this vector as 1. So that way we obtained the orthonormal basis for the subspace spanned by this initial 3 vectors. Okay. Okay, and then So although there are a few theorems in this chapter, but it is just enough to understand this this process intuitively. So it's not about like proving it rigorously, but it's more about the intuitive understanding about these process. Okay, so if we're given this basis vector, which are linearly independent, and then these are the also normal or orthogonal basis for the same space spanned by this linearly independent vectors. So we start with the first one, and then we optionally normalize it, right? 1 over v1, right? It's quite tedious just when writing it, but yeah, for the second one, we subtract this orthogonal projection on, and this guy will be the the next orthogonal basis vector, and then we can also normalize it, right? And then for the third one, we subtract the orthogonal projection onto the previous orthogonal basis vectors, and so on, right? And then finally, the span of these initial set of basis vector will be the same as the span of our orthogonal versions of the basis vectors. Okay, and then now we move on to this orthonormal one. And then now this guy is the main part of this chapter, this subchapter, which is called QR factorization. QR factorization. Okay, and then let's go back to this guy. Okay, this example. And then let's just try to. So what we are doing here is, suppose this matrix A is composed of the columns of the initial set of basis vector, and then we now change it to the orthogonal basis vector, also normal basis vector. So in this Q, what is Q? It is the same as this guy, U1, U2, and U3. Okay, so this is our Q. And then what we want to do in this QI factorization is we want to make A equal to Q times something. Then we have the first column of an x1, and this first column can be thought of as the linear combination of u1, u2, u3, and where is our linear combination coefficient? It will be the first column of the matrix R. Okay? And then what would be the linear combination coefficient here? What is the first element, for example? How did we change this x1, or how did we obtain this u1 using x1? x1 was, or u1 was this guy. And if we think about this x1, and then x1 will become u1 times this norm of x1, right? And so this first guy is x1. And what about the second and the third one? What is the linear combination coefficient? should be 0. Does it ever use u1 or u3, u2 or u3 to explain x1? Probably no, right? Okay, so this time is up already. So let me see. Okay, then let's postpone it after our exam. So our exam scope will be like up to 6.3 instead of 6.4. Okay? Okay, thank you very much. 네,
방금 여기서
네,
R을 나타내는
네, 맞아요. 이게 R이에요. 네.
근데 여기서는 R이 첫 번째인가
요거는요, 요거는 조금 다른 각도에서 구할 수 있는 거고요.
아 이거는 그냥 U와 X가 같은 다르게
네.
여기가 그냥 정규 단위 벡터
네, 그러니까 Q가 이제 U들로 이렇게 구성이 되는데 A를 이제 하나하나 이런 어떤 also normal 컬럼들을 얻어내는 거 썼잖아요. 근데 이거를 우리가 이걸 통해서 어떻게 하려고 그러는 거냐 하면 A에서 Q를 얻어낸 건 맞아요. 맞는데 이 Q를 가지고 다시 A의 하나하나의 컬럼들을 우리가 한번 나타내 보려고 하는 거예요.
아
그래서 아까 얘기했듯이 이렇게 뭔가 also normal 베이시스 벡터들을 얻었으면 원래 있던 이 좀 구부러지고 길이도 다 달랐던 벡터들을 우리가 얻은 이 also normal 베이시스 벡터들의 리니어 컨비네이션들을 한번 나타내 보려고 해요. 그렇게 되면 이게 이 Q가 이렇게 세 줄이 있고요. R에서 첫 번째 줄이 이게 세 개짜리 엘리먼트를 가질 거고 이 세 개짜리 엘리먼트를 가지고 X1을 만들어내야 돼요. 즉 그 말은 우리가 also normal basis 벡터들을 얻었으면 얘네들 갖고 우리가 갖고 있던 맨 처음 벡터인 x1을 한번 얘네들 also normal basis의 리니어 컨비네이션으로 한번 나타내보자 이거. 지금 그 복원 작업을 하는 거예요.
그냥 R은 그냥 개수만
R이 개수 매트릭스예요. 근데 그 개수가 이게 이제 리니어 저기 어퍼 트라이앵글러가 돼요.
네
네. 그래서 그것들을 이제 다음 시간에 좀. 아 이거 오늘 끝냈어야 되는데 지금. 네.
앞에서 3번 증명하는 뒤에 풀이가
아, 네.
얘는
이게 몇 단원이에요?
6-1
네.
장인데
네.
그래서 여기서 보다 보니까 이해는 갔는데 여기서 이게 왜 랭크 A가 되는지 콜룸
네.
A가 랭크 A로 기억을 했는데
아 저거요. 저게 그러니까 네. 컬럼 스페이스의 저기 랭크가 그러니까 컬럼 스페이스의 디멘전이 랭크라고 부르는 거잖아요. 근데 이제 디멘전 즉 컬럼 스페이스의 베이시스 벡터의 그 개수가 그게 결국 디멘전이자 우리가 부르는 랭크인데 그게 그러니까 로우들의 베이시스 벡터의 개수, 로우 스페이스의 베이시스 벡터들의 개수랑 똑같거든요. 왜 그러냐면 그러니까 기본적으로 콜 A 이거 우리가 랭크 A라고 불렀고요. 이거는 로우 A가 돼요. 왜 그러냐 하면 이 콜 A 컬럼 스페이스 오브 A의 랭크를 어떻게 구하느냐? A를 뭔가 이제 그걸 하죠. 그 에슐론 폼을 만들어서 그 피벗의 개수가 랭크였죠. 여기서도요. 이거를 한다는 거는 뭐냐면 이거를 A 트랜스포즈를 이렇게 뒤집어서 이거를 이렇게 뒤집어요. 그래서 여기서 이걸 하는 거가 똑같고 여기서 이걸 했을 때 여기서 나온 피벗의 개수가 이 로우 스페이스 A의 디멘전이 되잖아요. 그러니까 로우 스페이스 A는 이거는 컬럼 스페이스 A 트랜스포즈랑 똑같은 거니까. 그러면 이 넘버 오브 피벗이 A 트랜스포즈에서 이거 로우 리덕션을 했을 때 넘버 오브 피벗과 피벗의 개수와 그냥 A에서 로우 리덕션을 했을 때 넘버 오브 피벗의 개수가 이게 이제 똑같아져요.
아 이게 스퀘어가 아니더라도
네, 스퀘어가 아니더라도 왜냐면 이 계단을 생각을 해보면 이게 항상 대각선 아래로 가는 거잖아요. 그러니까 컬럼과 저기 로우를 하나씩 이렇게 좀 하나씩 먹고 들어가요. 그쪽으로. 그렇게 되면 네, 이게 그래서 갈 때까지 가는 게 뭐 이런 성질도 또 있어요. 이 랭크의 A는 min m, n 그러니까 5x4 매트릭스다. 5x4 매트릭스면 이 저기 피벗은 총 맥시멈 하긴 4개가 있을 수 있겠죠. 근데 만약에 4x5 매트릭스가 있어요. 그럼 이때는 피벗이 몇 개 있느냐? 아무리 많아봐야 4개밖에 없어요. 왜 4개밖에 없을까요? 그러니까
자유
그렇죠. 그 자유 프리 베리어블이 하나가 무조건 생겨야 될 거고. 그건 왜 그러냐면 이 우리가 이제 스테어케이스 이 계단 형태로 내려가는 게 항상 이렇게 대각선으로 내려간다 그러면 로우 하나 없애고 컬럼 하나 없애고 이렇게 하나씩은 일단 기본적으로 우리가 쓰고 들어가야지 되기 때문에 그렇거든요. 그래서 이제 이 계단이라는 게 어떤 이거를 로우 리덕션을 하나 아니면 이걸 이제 우리가 컬럼 리덕션을 하나 그러니까 이걸 뒤집어서 로우 리덕션을 하는 게 이제 컬럼 리덕션이라고 볼 수가 있대. 그런 경우에는 다 그냥 이거랑 피벗의 개수는 이렇게 놓나 이렇게 놓나 뒤집어서 로우 리덕션을 하나 그냥으로 로우 리덕션을 하나 피벗의 개수는 항상 똑같게 나오거든요. 그래서 요거 두 개가 똑같아지게 돼요.
아 이게 지금 당황해서 이게 좀
네, 이건 내가 좀 설명을 안 한 부분이네요. 진짜. 네.
지금 직선일 때 그러니까 직선일 때 그걸 올서 노멀이란 말을 쓸 수 있나요? 올서
직선일 때도 그러니까 베이시스 벡터가 하나밖에 없죠. 그러면은 하나짜리가 올소고널 하냐는 거는 하나짜리만 있을 때는 걔가 난제로면은 올소고널을 한 거예요. 근데 올소 노멀 하냐? 하나짜리가 이제 길이가 1이 되면 올소 노멀 하게 되는 거죠. 그래서 여전히 하나짜리에서도 그러니까 벡터 하나짜리에서도 우리가 리니어 인디펜던스를 따질 수가 있었듯이 난제로 벡터면 리니어 인디펜던트 한 거니까. 그러니까 이제 올소 노멀 혹은 올소고널 벡터를 이제 하나짜리에서도 그런 걸 따질 수가 있어요.
아 그럼 6-4는 지금 오늘 좀 어떻게 해야 되는 건가요?
6-4는 지금 시험 범위에서 제외를 하고 시험 끝나고 이제 더 진도로 나가려고. 네.
아, 저는 그냥 번외 질문이 있었는데
I will talk to you.
꽂아가지고 외장적 떴단 말이야. 그러니까 다음번에 막아버렸잖아. 거의.
걸어가면 혹시 시간 있으시면 그러니까 물어보고 싶은 게 있었는데요.
이거 리니어 알gebra
아, 그러니까
그럼 어떤 거?
그러니까 컴퓨터에 관해서
네.
그 컴퓨터 할 때 그 저장 공간 있잖아요.
네.
아니, 근데 먼저 하시면 안 돼요?
네, 그렇죠.
그러니까 저장 공간 있잖아요.
네.
그러니까 말하기 혹시 제가 그냥 걸어가면서